Say you're grinding a video game monster, like wither skeletons in Minecraft, for a rare drop. You know that the drop chance is 1 in 40 or 2.5%. So a couple minutes later, you're getting frustrated and you say, I killed 40 already, I should have gotten it by now. But you haven't. Well, what was the chance of that happening? And what is the chance that you do get the desired drop by the time you kill 40 skeletons? We will answer this question by the end of this video. But first, we need to gain a basic understanding of probability. Here's something seemingly unrelated. Imagine you look at the weather forecast for tomorrow and see this. There's a 2/5 chance that it's cloudy, a 1/5 chance that it's rainy, and a 2/5 chance that it's sunny. Now, what is the probability that there will be clouds tomorrow? Well, let's just go ahead and add up these probabilities. 2/5 that it's cloudy but no rain, plus 1/5 chance that it's cloudy with rain, equals 3/5 chance of there being clouds. Now, let's think of another example. Let's say you're flipping a coin twice. What is the chance that you get at least one heads? Well, can we do the same thing? You know that getting heads is a 1 in 2 chance. So just 1/2 plus 1/2 equals 1 equals 100%. No, you cannot do this. This is completely incorrect. But why? We added up the probabilities last time. So why can't we do the same again? Well, these situations are fundamentally different. In the first case, we say that we have dependent probabilities. If one of these events happen, the others cannot happen. If it's sunny tomorrow, it cannot rain. It also cannot rain and not rain at the same time. But here, the probabilities are independent. You are able to get two of the same outcome. You can flip heads heads or tails tails. Getting one tail does not mean that we cannot get another one. This means you cannot simply add up independent probabilities. We have to do something else. So, what is the actual way to solve this second example? Well, let's take a look at the first one. Notice that another way to get the answer is to do 1 minus the probability that it is not cloudy, right? Because if it's not cloudy, and we subtract from 1, we will get the chance that it is cloudy. So 1 minus 2/5, which is the chance that it's sunny, equals 3/5. The exact same as what we got last time. This is a very important concept that we will be using constantly. If we subtract the probability that something doesn't happen from 1, we will get the probability that it does happen. So, if we want to find the probability that we get at least one head, first we need to find the probability that we don't get a single one. Well, how can that happen? We need to not get a heads on the first attempt, which is a 1 in 2 chance, and we need to not get a heads on the second attempt, which is also 1 in 2 chance. Again, we can't just add these up, but notice that what we have is a half of a half, since we need both events to occur. A half of a half means 1/2 times 1/2, which equals 1/4. So the chance that we don't get a single head is 1/4. Notice that we can also express this as 1/2 squared. And these 2 and the exponent came from the fact that we did 2 attempts. If we threw the coin 3 times, we would raise to the 3rd power instead. So this is great. We just found out how independent probabilities combine. They multiply rather than add up, like dependent ones do. But we're not quite done. Remember, we wanted to find the chance of getting at least one head. So we subtract the chance that we don't get a single head from 1. And we get 3/4. This is it. We found the chance that after 2 throws you get at least one head. But is there another way to look at this? Well, let's consider a table of possibilities. Here on the top, we will have the result of the first throw. And we either get a heads or a tails. And here we will have the second throw. And we will get a heads or a tails. So, you might get heads heads, tails heads, heads tails, or tails tails. you can see that 3 of these possibilities include a head, and this corresponds to the 3/4 probability that we have at least one head. And here you can also see the reason that we cannot add up these probabilities. It's because we can get repeated results. If we say that you can't get the same result twice, you see that both of the possibilities include a head, which corresponds to the 100% chance that we incorrectly found at the start. So if you had some magical coin that could not repeat the result, then of course after 2 throws you would have at least one head. Now we are finally ready to tackle the opening puzzle. We will take the exact same approach as with the coin puzzle, so let's start by finding the probability of not getting the desired drop. Since the chance of getting it on any given try is, let's generalize a bit and say 1 in x. So for the wither skeleton example, this is 1 in 40, so x is 40. So the chance that you don't get the drop on any given attempt is 1 minus 1 over x. But this is after just one try. This is the chance that you don't have the drop after one try. So how do we find it after some number of tries? Well, since independent probabilities have to be multiplied, we will raise this to the number of the attempts. And since we are saying that we are doing x attempts, well, remember in the opening puzzle, the chance was 1 in 40 and we did 40 attempts. We will also raise this to the power of x. So if we just want the answer to the opening puzzle, we can just plug in 40 and get the answer by plugging into a calculator. But what I actually want to ask is what happens if x gets large? What if instead of hunting wither skeletons in Minecraft, you're instead gunning for the Rod of Discord drop from a Chaos Elemental in Terraria, which is a 1 in 500 chance? Or something even more absurdly rare, where x gets larger and larger. Well, mathematically, we can express this idea as what's called a limit. As x approaches infinity of 1 minus 1 over x to the power of x. What does this equal? This will correspond to the probability of not getting some rare drop after x attempts, if the chance is 1 in x. Let's mess with the inside expression a little bit. We can combine the fractions. We can flip the fraction and add a negative exponent. Now add and subtract 1 from the numerator. Now split the fraction. X minus 1 divided by x minus 1 becomes just 1. And we are left with 1 divided by x minus 1. Now, what if we multiply and divide the whole expression by this inside? Well, if we multiply by this expression, we simply add 1 to the power. But now we also need to divide by this expression to cancel it out. So we will multiply by 1 over this expression. And now to make this x minus 1 match this minus x plus 1, we will take out a factor of minus 1 from this exponent. Now this looks super messy, but notice that everywhere we have x, we actually have x minus 1. This means that we can replace x minus 1 with something else, like, let's say, n. Now remember, we will be taking this expression as x, or n, approaches infinity. And as that happens, 1 over n will disappear. And we're left with 1 over 1, which we can also cancel out. So now what we are left with, when we are taking the limit, is the limit. This minus 1 power we can write as 1 over what's left. 1 plus 1 over n to the power of n. And actually we can take the limit inside the fraction. And this limit in the denominator is one very famous limit, which evaluates to the number e, which is approximately 2.71828. And remember, we have 1 divided by this limit, so our intermediate result is that the probability of not getting the drop is 1 over e, or approximately 37%. And now we are finally ready to answer the main question. What is the chance that you do get the drop after x attempts? Well, it is 1 minus 1 over e, or approximately 63%. As I said in the first chapter, you simply cannot add up independent probabilities. Or can you? Well, to demonstrate what I want to show you, let me modify the previous problem a bit. Let's say you got super lucky. You got the 1 in 40 chance drop in just 2 tries. But just how lucky was that? Well, you can plug it into the formula we discovered recently. 1 minus 1 over 40 squared. This exponent 2 is because we got lucky and got it in 2 tries. And if you plug this into a calculator, you will find that it's approximately 4.9%. But is there a simpler way to understand this probability? Well, let's try to expand this bracket. And we will substitute 1 in 40 with 1 in x to be more general once again. 1 minus 2 times 1 over x plus 1 over x all squared. This 1 cancels with this 1. This minus becomes a plus. This becomes a minus. And what we are left with is 2 times 1 over x minus 1 over x squared. But notice, if x is a fairly large number, like 40, this fraction will be very small. And when we square it, it will become extremely tiny. So this is approximately equal to just 2 times 1 over x. Or 2 times the original chance. So, in our example, the original chance was 2.5%, and we will have 2 times 2.5% equals 5%. And notice that this is extremely close to what we got with the exact formula. This is because, once again, this correction factor of 1 over x squared is extremely tiny. And you can see that in this case, where the probability is small, essentially we can just add up the probabilities. We said that we have 2 tries and 2.5% plus 2.5% is 5%. Unlike in the case with the coin, because there the probabilities were much bigger, 50%. There you cannot get away with this, but because our probability is small, that means that the probability squared is extremely small, and we can just add up the probabilities. But what if you got it in 3 tries? Well, you can work through the math, and you'll find that it is approximately 3 times the original chance. And in general, 1 minus 1 over x to some power n is approximately n times 1 over x, as long as x is a decently big number compared to n. And what we have just discovered is called the binomial approximation, or at least its first term. Usually this is written as 1 plus x to the power n is approximately nx, which works when nx is a small number, much less than 1. You can see that 1 over 40 times 2 is 1 over 20, which is a small number, so our approximation holds. And this approximation gets better and better as nx approaches 0. But back to our example, this means that for small probabilities and low numbers of tries, you actually can just add up the probabilities. But is there a different way to look at this to gain more intuition? Well, think back to the table approach from before. The reason that we couldn't simply add up the 2 probabilities was the possibility of repeated results. But in this case, a repeated result would mean that in 2 attempts you got 2 of the rare drops, which is a very small chance, so we can safely ignore it, and go ahead and add up the probabilities anyways. So, to conclude, in this video we learned about dependent versus independent probabilities. We then learned the limit definition of the number e. And we also learned about the binomial approximation, all in the context of mob drops. I think this is a very fascinating topic since it leads you to all these different areas of maths, all of which are very useful in different fields. Now, as an appendix, I want to look at where the number e appeared in our problem. What we had is the limit, as n approaches infinity, of 1 minus 1 over n to the power n. And this is actually a special case of a different limit. You can see that in our case, x is equal to minus 1. And it turns out that this is exactly equal to e to the power x. So in our case, this is equal to e to the power minus 1, which is 1 over e. E to the x is another extremely special function. We can plug in any x and get e to the power x, which you will see all the time in all areas of mathematics. And this is where I will leave this video.